Hello, Honors Chem students. Mr. Keister here with you again. This is the video for Friday, September 11th, 2020, 9/11. I remember that day well. What a sad day that was. Back in 2001, I believe. Gosh, I can't believe it's been that long, but it has. Anyway, this is our scheduled 16th day of school for the fall semester. Keep in mind, though, that the dates could change based on a variety of reasons, but regardless of that, the lessons will continue in the same order. Okay, this is an intro video. It's not going to be too long to today's lesson. This has happened before, and it will happen again, because the curricula in your class and the curricula in Chem 2 do cross over. All right, they do cross over. So this lesson on density and specific gravity I have previously given, it's been a week or so ago in Chem 2. And so once you complete this, or once I complete and you complete watching this intro video, then you will then advance to the video on the actual lesson over density and specific gravity. And again, pay no mind to the do nows and the fact that the video says Chem 2 and all that, because that's not you. That's why we're doing this one here. I will tell you this. You will be able to, when you get to the next video, the video over the actual lesson, over density and specific gravity, you can push ahead through the first 2 minutes and maybe 5 or 6 seconds of that video. The information in that first 2 minutes does not really apply to Honors Chem. So if you want to skip on by that, you're more than welcome to. I would start right around 2 minutes and 5 seconds, and then the rest of the lesson is exactly the way it's going to be presented here in class. So, having said that, let's look at our schedule for today. So, your homework for today was to complete 1-2 Part C, any density. As I said yesterday, we're collecting that, and so you need to have that on my desk. If you're at home, of course, you need to submit it to me electronically. I do have an answer key posted with the data that I recorded when I did the lab, and that data, or that sample data, would be on the answer key that's either here on the board if you're at school, or posted to the answer keys page, which you can link from my campus homepage. So today we're going to talk about, right now in this little intro video, I'm going to talk about general problem solving, and then I will end this video, and then you will then go to the next one, which is over the actual lesson, or the main lesson today, which is density and specific gravity. And I will be collecting that for a grade on Monday. So you picked up a new notes packet today and the assignment over density and specific gravity. So let me unfreeze the board. There we go. And we're just going to talk a little bit in this intro about general problem solving and data relationships. So, problem solving, and we do a lot of that in chemistry. I mean, that's kind of the way it is. We record a lot of data, and then we analyze and process that data to solve a problem. So that's kind of what we do here. All right. Analyzing and solving scientific quantitative problems requires a logical approach. I was taught this approach by my chemistry teacher a long, long ago when I was your age, and it served me well there. It served me well in my advanced chemistry classes in high school, and it served me well at Purdue, where I took a whole lot of more advanced chemistry classes. It's a good approach. It covers all the bases, and most importantly, it gets you, or it allows you to receive full credit for all the problems that you're going to solve, because in many cases, full credit is lost because you don't show the amount of work that you're supposed to show. And so I'm going to cover that today, and certainly again on the main video over our lesson today over density and specific gravity. These are the 4 steps to the problem. It's called the APCE method. A stands for analyze the information. Basically what that means is you read the problem and you identify and label all the data and what it is you're trying to find. Okay. The P is plan. What method are you going to use? Proportional reasoning, conventional analysis, or what equations will the data fit into in order for you to solve the answer? And also, some data might not be listed but inferred. There might be a mathematical constant involved. There might be data you need to pull off the periodic table. So not all the data that you need may be given, but it's available to you. Okay? So basically, this incorporates listing the equation or equations or other method. Okay. Third, compute. Simple enough. Plug in the numbers. Solve. Round correctly. Depends on your math operation, right? And label. Label your answer. All right. And then fourth, evaluate. Examine your answer to determine if it's reasonable. This is one of the biggest mistakes people make. Now, everybody can punch the wrong buttons in the calculator, myself included, done it many times. And you get an answer that makes you kind of stop and think, now, wait a minute, does that sound right? And if you're thinking that, then it's probably not right. And even if it does seem right, it takes 10 seconds to run the numbers again or less. And so it's worth it. Believe me. Because people don't do this, I've gotten crazy answers every year on every assignment that should have never happened. We've been talking about density. All right, so the density, for instance, of copper, 8.96 grams per ml. So let's say that a student's doing a density problem involving copper, and they're trying to solve for density, and they're given some data, and they plug it in, run the numbers, and they get an answer of 3,250 grams per centimeter cubed. And you think, now wait a minute, 3,250? There's no way that can be right, right? And yet, somehow, they just magically think that whatever that calculator says is right 100% of the time, kind of like the internet, right? And then they run with it. So, and it costs some points. So, like I said, take 10 seconds, run the numbers again. If you get the same answer, fine. If you don't, then it's time to look maybe a little closely, all right? What I have done over here, and I'm going to go through this again in the main lesson, is kind of summarized this method over here. And that is going to be on the board from today until the end of the school year. It's that important, all right? It's a constant reminder of what you need to be doing when you're problem solving so that you can get full credit for all of your work, all right? I will go over that again in the main lesson today. So next I would like to talk about some general relationships between data, and that's then going to finish up this intro video. First one is direct proportion. There's a lot of these, all right? Two quantities are directly proportional to each other if dividing one by the other gives a constant value. In other words, the ratio of the two always gives you the same value. As one quantity increases, the other is going to increase by the same amount, because when you divide one by the other, you keep getting the same answer. Well, that ratio between numerator and denominator has got to be the same, all right? The graph of a direct proportion is a straight line with positive slope. And the slope reflects that constant ratio. If this sounds familiar to you, it should, all right? Because an example of a direct relationship is the direct relationship that exists between mass and volume, all right? And the ratio of mass to volume is a constant, and we call that constant density, all right? So let's graph this again. We've done it before, real quick. So here we have mass and volume, all right? course, 0, 0, talked about that. That's a good point on a density graph. So let's say we have mass 1 here, and then we find its volume, and it's right here. All right? And so there's that point right there. And then we take a second mass, a different one, let's say a larger one, and here's mass 2, right? And then we come over here and we find, about yay there, volume 2. And if we graph that point, it's right there. And we, of course, this isn't perfect. I didn't think it would be, but I tried. All right, there we go. I'll make my dots bigger. That'll fix it. All right. And here you have our straight line, positive slope, and the slope reflects the ratio between y and x, which in this case is mass and volume, which means the slope is equal to density, as we've said before. Right? Slope equals density. And it's from this graphical relationship we said that d equals m over b. And there is that ratio, all right, mass to volume, and it gives us a constant d, all right, which in this case is d. One other thing, the ratio of y divided by x is a constant, meaning they're equal. So let's look at this. So here's mass over volume at this point, mass 1 over volume 1. The ratio of there, we're saying, is the same as the ratio of mass 2 to volume 2. Same ratio on the same line, aren't they? Well, then the ratio is the same. The density of this line is constant. So we could also say this right here. This is the general format, m1 over b1 equals m2 over b2. This is the general format of a math equation for any direct relationship between two variables. Now the letters may change, all right? We have a law in gas behavior, Charles' law, that says the volume of a gas is directly proportional to its Kelvin temperature, and there's the equation for Charles' law. If you look, it looks exactly like this, except different letters. That's what I'm trying to say. Any direct relationship between two variables is going to end up having a math equation that looks exactly like those. All right? Just to reiterate that, all right? The dividing one by the other, y over x, yields a constant value, meaning any point on that line, that ratio of m over b in this case is going to be the same as any other m over b on that graph. Okay? And the last one I want to talk about is in inverse proportion. An inverse proportion. Two quantities are inversely proportional to each other if their products are a constant. Remember, a direct proportion is y over x, or one divided by the other is a constant. Here, their product is a constant, all right? As one quantity increases, then the other decreases by its inverse. So if one doubles, the other one's cut in half. If one quadruples, then the other one is 1/4 of its original. If one increases by a factor of 8, the other is 1/8 its original value. 2 times 1/2, 1. 4 times 1/4, 1. 8 times 1/8, 1. Multiply them together, you get a constant value. All right, a constant value. The graph of an inverse proportion is a hyperbola. You guys remember what a hyperbola looks like? Like that. All right, let's graph one. Pressure versus volume of a gas. All right, so here's P and here's V. So let's say we have we're going to record a pressure, and it's a very high pressure, and yet the volume is very low. So let's see, it's right here. So look, P1 is quite large, and B1 is very small. All right? And then we have another one, let's say about right here. Here's P2, which has gotten smaller, and B2 has gotten larger. Then we have another one down over here. B3 has just gotten smaller, and B just keeps getting bigger. And the product of P and V, wherever you are on this graph, is equal to the same value. It's constant. And this is how it graphs, like so. Right? They approach the axes, but never hit them. So the product, all right, the product of an inverse relationship between two data is a constant. So basically what we're saying is, so here's point P1 and B1. So P1 times B1 is equal to, right here, the product of P2 times B2. See how that equation is different than the one for a direct proportion, all right? The product of P and B here and the product of P and B at a different location on that same graph is equal to the same value. This is actually the equation for Boyle's law in gas behavior relationships. Boyle's law. The volume of a gas is inversely proportional to the pressure placed on the gas or the pressure the gas exerts on its container. And there are other derived equations involving inverse relationships that look exactly like that, only, of course, with different variables, different letters. So that's where I'm going to end the intro to today's lesson, all right? So now you will proceed to the video that entitled Density and Specific Gravity. Again, it's going to say it's a Chem 2 video. Don't worry about that. It's the same lesson. Like I said, you can scoot it forward about 2 minutes or so to where the actual lesson begins. So until next time, so watch that one. Pay attention. I'm going to talk a lot about this right here, how to show your work properly in solving problems involving density and specific gravity, and also in the future. Pay very close attention to that. It's extremely important. So until next time, this is Mr. Keister signing off. Head to the next video and watch today's lesson, and I will catch you next time. Take care, everybody.